Hello everyone, my name is Wang. In this video, I will introduce a new lightweight in-situ adversarial sample detector for DNN. Now let's first get to know what an adversarial sample is. An adversarial example adds visually imperceptible perturbations to a clean image that can delude a DNN classifier into wrong predictions. You may think, well, how dangerous is this? Let me give you an example. Here is a stop sign. Then because of this added adversarial perturbation, a self-driving car may perceive this stop sign as go, and a car accident is very likely to occur. Existing detection methods are mostly software-oriented. Hardware-oriented methods are very few. Then what is the difference between these two? Software-oriented methods are realized by computer programs, where both the deep learning network and detection are simulated on CPU or GPU. Floating point arithmetic is applied. Therefore, they are often compute-intensive. Hardware-oriented methods focus on resource-constrained platforms, where dedicated hardware accelerators are necessary for efficient DNN processing. Fixed-point arithmetic is adopted. Therefore, it is quite hard to adapt software-oriented methods to those resource-constrained platforms. Then, with the computing paradigm shifted to edge, where data are generated and processed locally, it is urgent to work out a hardware-oriented solution that is lightweight enough to be integrated into an edge AI platform. Of course, it should also maintain a good detection performance. Our work mainly utilizes a clock glitch as a controllable uncertainty to blindside the adversary. Our hypothesis is that for clean image input, glitch injection may result in the same prediction, but different for an adversarial input. To verify this hypothesis, we use the circuitries shaded in gray for glitch injection to DNN computations. We inject glitch layer-wise to also investigate the layer difference. The results are shown here. We find out that adversarial images are indeed more likely to change predictions upon glitch injection. And for each layer, there tends to exist an optimal point that maximizes the difference between adversarial and benign inputs. This somehow gives some hints for how to better differentiate adversarial from benign inputs. We can find out some glitch patterns with large delta LCP. We can also utilize more information besides label change, such as probability, to train a detector, and finally deploy the detector. And these are exactly the main procedures for our proposed method. First, we use the following formula to find out the candidate glitch patterns. Then we collect three kinds of probability information correspondingly: original, mutated, and difference. Then we construct a database like this. We use such database to train a detector. Two kinds of decision tree algorithms adopted for training: classical one and lightGBM. The main difference is the tree growth manner, as shown here. Finally, we integrate the already trained detector to the deep learning accelerator for in-place detection. Here shows the detection performance. We can see that lightGBM generally performs better than classical decision tree, and the method is more effective for deeper networks. And among all the attacks, it is more effective against universal perturbation attack. Compared with existing software-oriented methods, our work has achieved the edge implementation, of course, and such substantial improvement in performance. Compared with the hardware-oriented schemes, our work has solved the scalability issue and implemented on a physical DNN accelerator with much lower overheads. With this, we come to the end of this video. Edge AI opens up many new application possibilities. Therefore, it is also important to secure it from adversaries. Our work clearly serves as a step forward in enhancing the security of Edge AI applications. That's all. Thanks for your attention.